All right, welcome back. We're going to take a look at the part two of polar versus nonpolar molecules. Okay, so there are situations in which molecules can have polar bonds, but the whole molecule ends up being nonpolar. And so let's take a look at an example here of carbon dioxide. So carbon is going to make a polar bond with oxygen in this direction. And so that is going to result in a partial negative charge over here. It's also going to make a polar bond in that direction, resulting in a partial negative charge on that side. If the bonds are polar, but the partial charges are distributed evenly across the entire molecule, then we say the molecule is nonpolar. And so this is an example of a nonpolar molecule. There's no distinct positive or negative end because the positive is stuck in the middle. The ends are all negative. There's no positive place. So if water molecules were to come in and try to interact with this, there's no real way for the water to come in and try to get to that carbon because it's surrounded by negative charges. So as the oxygens from the waters come in, they get repelled by all of these electrons. You have to remember that there's pairs of electrons out here in these oxygens that are going to be repelling any other electrons that try to get close. So if the bonds are polar, but they are evenly distributed across, and there's no distinct positive and negative end, then we say the molecule is nonpolar. So you're looking for symmetry. Is the molecule symmetrical? And in this case of carbon dioxide, it is. So let's take a look at a couple of others here. So this is carbon tetrafluoride, carbon with 4 chlorines attached. All 4 bonds are positive, but notice that it's symmetrical in every direction. The partial positive is stuck in the middle right here, and there is no way for a negative water or something else to get into the center of that. So all the bonds are polar, but the molecule is nonpolar. You're looking for symmetry across the entire molecule to make that decision. Take a look at this one, boron trifluoride. Again, they're all going in 3 directions. The positive is left here in the middle, and it is symmetrical. So we would say that that molecule is nonpolar. So you're looking for uneven or non-symmetrical molecules. So if you take a look and compare water and carbon dioxide, both molecules contain 2 polar bonds. They both go out from a central atom. But notice that the geometry is different. Carbon dioxide is linear. Water is bent. That results in a difference in the symmetry such that the molecule one is polar and the other is not. Here, there is a distinct negative end to it. It's sitting up here, and then this area down here is positive. So you can say that there's one end that's negative, one end that's positive because of that bent nature of it. But if you make it linear, there's no distinct positive or negative ends to it. It's symmetrical. So you're trying to look for asymmetries that allow for this positive or negative end to develop. Okay, so you're going to give it a try. I would get out a sheet of paper, and I want you to pause the video as we go through each one of these. I want you to draw the molecules, examine the bonds, and see if you think they're polar or nonpolar. And then we're going to determine, are these polar molecules or nonpolar molecules? Let's start with C2H4, and I'm going to run through this one with you, and then I'm going to let you try to figure out the next one. So this is what the molecule looks like. We know that the carbon-fluorine bond is polar. And pretty much anything with fluorine is going to be polar. It's the most electronegative atom. So we know it's going this way, and we know it's going this way, and we know it's going this way. So we've got 4 polar bonds. We have a nonpolar bond in between the 2 carbons. What do you think? Is it polar or nonpolar? Well, this is a symmetrical molecule. So even though there's 4 polar bonds, we are going to say this is a nonpolar molecule. Okay, your turn. Pause the video, draw it, see what you think. All right, we're back. Let's take a look. HCl. HCl is a linear molecule, but there's a distinct positive and negative end. The bond between hydrogen and chlorine is definitely polar, so there's going to be a positive side right here, and there's going to be a negative side right here. Now you notice the way we're drawing the arrows here? So the arrows give us a sense for where the electrons are going, and the way we do this is we point the arrow toward the more electronegative atoms. We point where the electrons are going, and we say the arrow head is the negative side, the partial negative side. Then we put this little hatch mark next to the end of the arrow, and that indicates that that's the positive side. All right, try NH3, ammonia. Pause the video, then draw it, look at the bonds, determine if it's polar or not. All right, we're back. Let's take a look. So in NH3, there are 3 hydrogens. All of the bonds are polar, so the hydrogens are all going up toward the nitrogen. The electrons are, at least. But we have to remember that nitrogen also has a pair of electrons at the top here. And that pair takes up space, so that pushes the hydrogens down. Just like a water molecule is bent because of those lone pairs, ammonia is also bent downward. And that results in a polar molecule because the positive end is on the bottom near the 3 hydrogens, and the negative side is at the top near that lone pair. All right, let's try BF3. Again, pause the video, draw it, take a look at the bonds, determine if it's polar or nonpolar. Okay, we're back. Let's take a look. Here, all 3 bonds, again, are polar. They're going out toward the fluorines, but because it is symmetrical in all directions, this is a nonpolar molecule. All right, we got one more to check out here. CH3Cl, so carbon, 3 hydrogens, and a chlorine. Pause the video, draw it, examine the bonds, determine if it's polar or nonpolar. All right, we're back. Let's see what you got. So in this case, we have an area that has 3 nonpolar bonds. So this is kind of a nonpolar part of the molecule. But there is definitely a polar bond between the carbon and the chlorine, and it's pointing upward. So that definitely makes for a negative end up here. And that's going to result in a positive end down here. And so this is definitely a polar molecule. There's a distinct positive and negative end. All right, let's do one last one. Take a look at this molecule. This is alanine. It's one of the amino acids that makes up the proteins in your body. And let's look at these. So white is hydrogen, black is carbon. Red is oxygen, blue is nitrogen. Is it polar or nonpolar? Well, I want you to start to realize that anytime you start seeing oxygens and nitrogens, you should be thinking to yourself, there's a good chance this is polar because those 2 are very electronegative atoms, so they like to make polar bonds. The other thing you should think about is, are they sticking out somewhere? Are they making distinct positive or negative ends to them? Well, in this case, they are not embedded in the middle, they're sticking out. And so you can actually identify locations where you've got positive and negative ends. So for instance, there's definitely a negative end out here, that oxygen's sticking out there. This nitrogen's sticking out over here, so you got to think about, can water molecules or any other polar molecules come in and dock with it? Yes, right here they can. These hydrogens are sticking off of that negative nitrogen, so yes, those are positive there and there. We've got this OH bond, so that definitely makes for a negative and a positive. And then you've just got this random O sticking out here, and that's definitely going to be negative, resulting in this right here being positive. So yes, it is not just polar, it's very polar. There's lots of places for water molecules to come in and dock. All right, try this one. This one's kind of interesting. The SC bond is nonpolar. So this entire molecule is nonpolar because there are no polar bonds in the molecule. So nonpolar. How about that one? You start seeing oxygens with all these lone pairs sticking out there? Yeah, it's polar. So this side right here is positive, and this side is negative. All right, our last one for this video is glucose. Glucose is full of oxygen and hydrogen bonds. And every time you start seeing oxygens and hydrogens together, you know it's going to be polar. So you can see on here, look at how many positive and negative ends there are to it. There's negative positive up here, there's negative positive right here, there's negative positive here, there's negative positive here, there's negative positive. Glucose is super polar. Lots of waters can come in and surround the glucose molecule, which is one reason why glucose is easily dissolved in water and can be dissolved into your blood and be transported to all the cells of your body for all your metabolic functions. All right, so that is how to determine whether molecules are polar or nonpolar.